Greetings, this is Mr. Pfeiffer. Let me start my timer. All right. So this is a makeup video just to keep us on track. This first one is for pre-cal. So let's just take a look at it. So we're going to go for about 30 minutes and then, and we'll see how it goes. So this is section 6.1, sequences in series. The word sequence is used in math in much the same way it's used in ordinary English. If a person saw a sequence of bad movies, then that person could list the first bad movie, then the second bad movie, and so on and so on. So an infinite sequence is a function whose domain is a set of positive integers. The function values are written as a1, a2, a3, an, so on and so on. These are called terms of the sequence. The nth term, a sub n, is called the general term of the sequence. If the domain of a function consists of only the first n positive integers, then the sequence is called a finite sequence. All right, so if we look at this example 1, it says write the first four terms of the sequence with the general term an equals a negative 2 to the n, okay? So when n is 1, all right, that means a1 is going to be negative 2 to the 1, but then that's just going to be negative 2, okay? Because if we do order of operation, we have to do exponents before multiplication. So we would say 2 to the 1 is 2, then multiply by a negative 1. Same for this one. It's because of the way it's written. Notice that it's not written in this fashion. If it was written in this fashion, like on example 2, when we say negative 2 squared, then it would be positive 4. But here we're going to say negative 2. We're going to say negative 2 squared, and this is going to give us negative 4 in this case. Okay. So then a3, we're going to get negative 2 cubed, and it's going to give us negative 8. And then a4, we're going to say negative 2 to the 4. It's going to give us negative 16. And a5, negative 2 to the 5th, negative 32. Okay, these are the first 5 terms of that sequence. So then in example 2, we're asked to write a general term for a sequence whose first 5 terms are this. So we want to find the general term, okay? So let's see, the first term, notice that the first one is 0, the second one is 1 over 2, okay? So when n is 1, we get 0, okay? I'll let that be. Now when n is 2, the result, so the denominator is n, we have a negative, and the signs are alternating, so we need to do something like negative 1 to the power of n plus 1, right? And then we're going to say n minus 1, okay? So now let's see if this works. When n is 2, the denominator is now 2, the numerator is now 1, and the exponent is and the exponent on the negative is odd, so now our function is going to be negative. So it looks like an might be something like this. Now let's test it out. So if we say a1, right, that's going to be 1 minus 1 over 1 to the times negative 1 to the 1 plus 1, right? So then that's going to be 0 times a positive 1, which is just 0. Okay, so that checks out. So then if we do a2, that's going to be 2 minus 1 over 2 times negative 1 to the 2 plus 1. So then this one's going to be, that's 1/2 times a negative 1, and we get our desired result. A3 is going to be 3 minus 1 over 3 times a negative 1 to the power of 3 plus 1. So now it's positive, and it's going to be a positive 2 over 3. Checks out. We'll continue over here. So then A4 is going to be 4 minus 1 over 4 times negative 1 to the power of 4 plus 1. It's going to be 5, so it's going to be a negative 3 by 4, which checks out. And the last one for A5 is going to be 5 minus 1 over 5 times negative 1 to the power of 6 So it's gonna become positive. We're gonna get a positive 4 by 5. Okay, and so on and so on. So we'll continue. So this general term, and I guess it might be a little bit better to write it in the following way. Let's just put the negative part first, and then put the second. But it still is the same thing, and it works. Okay. So recursive formulas. Up to this point, we have expressed the general term as a function of the position of the term in the sequence. A second approach is to determine a sequence recursively. A recursive formula requires that one or more of the first few terms of the sequence is specified, and all other terms are defined in relation to the previously defined terms. So, for example, the Fibonacci sequence is a famous sequence that is defined recursively. It shows up often in nature. Okay, in this sequence, we specify the first two terms. A1 is 1, and A naught is 1, and A1 is 1. Okay, so then the remaining terms are as follow. So A naught is 1. Let me see something. I feel like that's a typo. A1 is 1. So then A2 is 2. A3 is 3. Okay. Where is it? A naught plus A1 is 2. Hold on. Let me see if I can load this book really quickly. I don't know if I have it here. I might have it here. I should. And if I don't, I have to go to the web to load it. And scrolling through here, I don't know if I'll see it or if I can find it. All right, let me go to P. Oh, there's one. I think that was calculus. Come on. Yeah, that's calculus. Let's keep going. Skip all this. So let's go. Anyway, I'm not going to worry about that. But, it's in the text. It's just the little tick marks I know is a typo, and it's kind of throwing me off. But anyway, so let's get back to it. So the first 6 terms of the sequence are, we have 1, 1, 2, 3. So we have 1, 1, 2, 3, 5, 8, right? The sequence can also be determined by the subscript notation. A naught is 1, A1 is 1. Then AK is going to be AK minus 2 plus AK minus 1. So it's the sum of the previous 2. So then A2 is going to be A naught plus A1. A3 is going to be A1 plus A2, so on and so on. Okay, so that's just an introduction to recursive. I was just trying to clear up those. I'm looking at it. I know those are some kind of typo, or I'm not sure what those tick marks are, but I was going to clean those up, but that's okay. So if we're looking at this example, it says write the first 5 terms of the recursively defined sequence. Okay. So we want the first 5 terms. So now I think A1 is given as negative 3. So then A2, if we use the formula, is going to be 2 times the previous, which is going to be 2 times A1 plus 5. So that's going to be 2 times negative 3 plus 5. That's negative 6 plus 5. It's negative 1, right? So then A3 is going to be 2 times A2 plus 5. So that's going to be 2 times negative 1 plus 5. Negative 2. It's going to be 3. So it looks like we're increasing by, well, that one we increased by 2. Let me look at it again. Negative 6 is negative 1. It's negative 2, that's a positive 3. That one we increased by 4. Let's do another one. So then we say A4. I feel like I might have made a mistake somewhere. So if we do A4, it's going to be 2 times A3 plus 5. It's going to be 2 times 3 plus 5. 6 plus 5 is 11. So that one increased by 7. So maybe it's just not behaving the way I think it is. So then A5 is going to be 2 times A4 plus 5. It's going to be 2 times 11 plus 5. It's 22 plus 5 is 27. Okay. So these should be the first 5 terms of the recursively defined sequence. And I think I have some old notes here where I can check. Negative 1, 3, 11. Yeah, these are good. Okay, so we got the same thing as the years in the past. All right. Let me see what my time is looking like. All right, cool. So factorial notation. Factorial for any positive integer n factorial, written as n exclamation mark, is defined by n times the previous, times the one before that, times the one before that, and keep that pattern until you get down to 1. Okay? And so as a special case, 0 factorial is defined to be 1. So we're asked to simplify. Okay? So if we're looking at 4a, we have 13 factorial over 12 factorial. This means 13 times 12 times 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1, divided by the same, minus the 13. So we're going to take these. Okay, so 12 factorial is that, right? So now, if we were doing this operation, notice all of this is going to cancel all of this. And then I want you to also notice that we could have also written it in this way. 13 times 12 factorial over 12 factorial. So then the idea is that this is going to cancel that. In either case, we finish with 13. Okay? But then if we look at 4b, so it has, we're doing n factorial over n minus 3 factorial. So what is n factorial? It's going to be n times the one before that. It's going to be n minus 1 times the one before that. It's going to be n minus 2 times the one before that. All the way down to 1 is going to be n minus 3 factorial. This is going to be n minus 3 factorial. So then notice this is going to cancel that. And then we just get n times n minus 1 times n minus 2. Okay. Oh, I think these are both okay. We get 13 and that same thing. Okay. Moving along. So in this example 5, we're asked to write the first 5 terms of the sequence whose general term is this. Okay. So then A1 is going to be negative 1 to the power of 1 times 2 to the 1 over 1 factorial. Okay. So there's going to be a negative 2 in the end. A2, negative 1 squared, 2 squared over 2 factorial. So now it's going to be positive. It's going to be 4 over 2, which is 2. A3, negative 1 cubed times 2 to the power of 3 over 3 factorial. 2 to the 3 is 8, so it's going to be a negative 8 over 3 times 2. But the 2 can turn the 8 into a 4, so then we'll finish with negative 4 by 3. So So then if we do A4, it's going to be negative 1 to the power 4 times 2 to the 4 over 4 factorial. So negative 1 to the 4 is going to make it positive. 4 times 4 is 16 over 4 times 3 times 2 times 1. Now, the 4 turns the 16 into a 4. The 2 turns the 4 into a 2. And I think that's the most canceling that we can do. So then we're left with a positive 2 over 3. And the last one, A5, negative 1 to the 5th, 2 to the 5th over 5 factorial. So we know it's going to be negative, and we have 5 2's, 1, 2, 3, 4, 5. The bottom is 5 times 4 times 3 times 2 times 1. Now watch. So I did a little different here, so you can see how we cancel instead of getting the big numbers, right? So the 4 is going to cancel 2 of the 2's. This 2 is going to cancel this. That's everything that's going to cancel. So now, if we write what's left over, we have negative 4 over 15. All right. And I think we have the old results somewhere nearby. So that one, we got the same thing, the negative 4 by 15. Do we need to move it again? I think so. Yeah, that looks better. And then this one, we got our negative 2, we got 2, and we got negative 4 by 3. And we got the 2/3. Yeah, so we're good to go. Okay, so we got the same thing as the years in the past. Okay. So then summation notation. The sum of the first n terms of a sequence, A1, A2, A3, AN, and keep going, is denoted by the sigma notation. So we have the sum as I goes from 1 to n of AI. So that means we're going to say A1 plus A2, or A of when I is 1, or A1 plus A2 plus A3, so on and so on until we get to AN. That's summation notation. Okay? So then the letter I in the summation notation is called the index of the summation. And n is called the upper limit, and 1 is called the lower limit of the summation. Oh, this one. I think it might be, is it here? Yeah, so let's, we need that part. Negative 1, find the following sum. 0 to 3, negative 1 to the k, k factorial. So it looked like it was negative 1 to the k, I can't remember, k factorial and 0 to 3. It's k factorial, and the sum, as this goes, as k goes from 0 to 3, I think that's everything. Let me look at it one more time. K goes from 0 to 3, negative 1 to the k. Okay, so we're asked to find that sum. Okay, so let's do when k is 0. So when k is 0, we're going to have negative 1 to the 0 times 0 factorial. That's the first one. Then it says do the next one. So we're going to say plus, when k is 1, negative 1 to the 1 times 1 factorial. Then 2, negative 1 squared times 2 factorial. And then we stop at 3. Negative 1 cubed times 3 factorial. If we keep going, negative 1 to the 0 is 1. 0 factorial is 1, so that first term is 1. Negative 1 to the 1 is negative 1. 1 factorial is 1, so that's just going to be negative 1. Negative 1 squared is positive. 2 factorial is 2, so that's 2. 3 factorial is 6, so that's going to be a negative 6, all right? So then these guys cancel each other. That's going to be negative 4. Negative 4 is good. Okay. See the time. So some summation properties. The sum of a constant, the first n terms, or the sum of a constant added up n times is going to be the constant times n. A constant times the sequence. Well, if you have a constant and you're adding up several times your term, you can actually factor out that constant and move it to in front of the sum. So we can factor out the constant and move it to in front of the sum. The sum of the sequences is the sequences of the sum. The sum of sequence A plus sequence B is going to be the sum of sequence A plus the sum of sequence B. So it's really using the associative property of addition, because if we wrote those out, we can break them apart with, again, it's associative property of addition, rearrange them, and then reorganize it so that it matches the right. Similarly, for the negative, for part 4, it's the same thing, because subtraction is nothing but adding a negative, so the same property holds. So then if we have the sum of a sequence as k goes from 1 to n, well, it's the sum of that same sequence as k goes from 1 to j, and then plus the sum of that same sequence as k goes from j plus 1 to n, where j is between 1 and n, and all it is like it's a point. We can just basically break the summation up into multiple parts. So we can add like the first part, and then we can add the second part. So we're breaking up to multiple summations. So then a series, we all know how to add numbers, but do you think it's possible to add infinitely many numbers? It's sometimes possible to add infinitely many numbers, although a complete explanation of this kind of addition must be put off into calculus. For now, we have some definitions. So we have A1 to AK and on. This is going to be an infinite sequence. Notice that the last thing in the sequence are ellipses, so it says to continue the pattern forever. So the sum of all terms of the sequence is called a series, and is denoted by the sum as I goes from 1 to infinity of AI. Okay. Then the sum of the first n terms of the sequence is called the nth partial sum of the series. It is denoted by A1 plus A2 up to AN, and it's going to be the sum as I goes from 1 to n of AI. Okay, so we're asked to write the following in summation notation. So we want to find a general term an that's gonna generate the sequence and capture the alternating signs. So now let's just do like how we did in the beginning. So if n were 1, we need it to be positive. So we're going to say -1 to the power of n plus 1, right? And it looks like we're saying 2n for this part. Okay, and our claim is that this is our an. Let's see if this works, if this generates the sequence first. So now the first one is going to be -1 to the power of 1 plus 1 times 2 times 1. So that's going to be positive, and it's just going to be 2. It checks out. A2, -1 to the 2 plus 1 times 2 times 2. It's going to be -4. So that checks out. A3, -1 to the 3 plus 1 times 2 times 3. We know it's going to be 6, and it's going to be positive. Okay, that checks out. So on and so on. So it seems like it's working. We're going to stop there. So now let's write this in summation notation. So we're going to say the sum, we're going to say a sub I as I goes from 1, so 14. Let's see, 1, 2, 3, 4, 5, 6, 7. As I goes from 1 to 7. Let's write it like the following. Instead of a sub I, we're going to say of -1 to the power of I plus 1 times 2i. So now we plug in a 1, we get our result. Then we're going to say plus the next one, plus the next one. I think this should be it. Let me check my old notes. -1, I plus 1, 2i. Okay, so yeah, this is good. Let's put it back. Okay, so this will do the nth partial sum. See what the time is looking like. Okay, let's go for a few more minutes. Actually, you know what? That's honestly a good enough stopping place. We don't have much time left, and I don't really want to get into this next section. So let's do the following. Okay, I'm gonna add a page, and I think we're just gonna go ahead and load a copy. I'll load a copy of this to Box, and so you'll see it. And let's see. You should have something else for the remainder of class to work on. All right. So, gentlemen, have a good weekend. Keep in mind that extra credit opportunity is still there. Just to remind you that I more than likely won't be able to go live, and I'll get your study guides and things posted for next week's exam. But on that note, we will stop here and finish out the class and enjoy the rest of your weekend. I am available by email for questions, and I'll just have to get to it as soon as I can. I will be busy, but keep that in mind. All right, gentlemen, have a good weekend.